All right, welcome back. In this video, we're going to be revisiting the idea of the linear transform. And today we're going to be talking about transforms really generally, and I guess functions really generally. We're going to be talking about functions that are one-to-one and onto, or injective and surjective and bijective. And this is a topic that comes back a lot if you keep taking more and more math classes. This comes back again and again in a variety of areas in math. So we'll start with the idea of one-to-one. And we'll say that a function f, and let's be really general here, which takes a set A into a set B, is what we'll call one-to-one or injective when f of a1 equals f of a2 implies a1 equals a2. And this is a little bit of a dense definition, but what this means is that we have no repeated outputs. The only way that we can have equal outputs is by actually having equal inputs. Okay, so let me show you, take it back to the y equals f of x world and show you a couple of examples, one that yes is injective and one that no is not injective. So let's start off with f of x equals x squared. It's a graph we know. It's very familiar. This thinking about unique outputs is equivalent to running a horizontal line test that feels a lot like the vertical line test you did in Algebra 1 a long time ago. So if we run a horizontal line through this parabola right there at a positive y value, we're going to intersect the curve at two places. That means we had a repeated output. Okay, f of 2 is the same as f of negative 2. That means that this function f is not injective, right? Because we had repeated outputs. But if I, switch my perspective a little bit and think about g of x equals 2 to the x, this one is going to be injective, because if I run a horizontal line through, I have, at most one intersection. Okay, and it's all right if I go down here and I have no intersections. That's fine. As long as I don't have repeated outputs, that would make a function injective. Now, we're interested in linear transformations here. In our linear algebra class, these are the functions we care about. So we're going to write a definition that would define what does it mean for a linear transformation to be injective. And so we know that we need to have no repeated outputs. And so we're going to say if a transformation takes Rn into Rm, which means it does have an m by n standard matrix, it'll be one-to-one if the system Ax equals b has at most one solution for each b in Rm. And so we think about at most one solution, that's either a unique solution or no solution. We can't have infinitely many solutions. And then the condition that we're going to look at to see if a given linear transform is one-to-one or injective is the nullity of the transform or the nullity of the associated standard matrix equal to 0. Okay, and I'm going to try to explain to you why this is true. Okay, so we're going to start by thinking about, just solving the system Ax equals b, right, with row reduction. And we said at most one solution. So that means either one solution or a unique solution or no solution, never infinitely many solutions. So if we think about how infinitely many solutions happens, if we have Ax equals b having infinitely many solutions at any non-zero b, then the homogeneous system Ax equals 0 is also going to have infinitely many solutions. That's necessarily the case. And you can see how that is. If you're getting infinitely many solutions with your row reduction with non-zero numbers to the right of the vertical bar, you're going to get infinitely many solutions with all zeros to the right of the vertical bar. It's more of a property of the columns of the matrix in the first place than it is like the output that you're putting to the right side and row reducing with. Okay, so this means that we can just check the number of solutions to the homogeneous system Ax equals 0 to see if we're going to be injective or not. And that's why I jumped straight to the nullity of the associated matrix. Okay, from here, I'm going to remind you that Ax equals 0 is never inconsistent because x equals 0 is always a solution. So we're never going to have to worry about no solution. So we really are interested in the situations where the homogeneous system has a unique solution. Okay, if Ax equals 0 has a unique solution, t will be one-to-one. Ax equals 0 never has no solution, and if it has infinitely many solutions, t won't be one-to-one. So this is got it narrowed down. And so this is going to tell me, okay, if that's the case, then the null space of A is the 0 vector only, and that's how I know that the nullity of A is 0. The basis for it has just the 0 vector. There's no dimension there. Or a basis for the null space has, no non-zero vectors in it, and that's why the nullity of A is equal to 0. But this also means I can apply the rank nullity theorem. A is a n by n matrix. It's got n columns. That does mean that the rank of A would be n. And if the rank of A is equal to n, I have n pivots and n columns. That's a pivot in every column. And so, when you're going and row reducing, that's really it's kind of down the line. This is a symptom of, the nullity of A being 0. But when we're looking for is a given transform injective, but what we're actually looking when we're looking at a reduced matrix is there a pivot in each column? If yes, then the associated transform would be injective. All right, let's move on to onto or surjective. A function which takes A into B is what we would call onto or surjective, or we would call it a surjection. If for all B in the codomain, elements of the codomain, B is equal to f of A for at least one element A in the domain. Okay, and so that means that all of the possible outputs are hit. The function is filling up the entire codomain. There's all sorts of descriptions for this. But I think I'm going to, once again, take it back to the y equals f of x world and show you a couple of examples that we might be familiar with. Start with f of x equals x cubed minus x. This is just a nice third-degree polynomial. It goes up, then down, then up. It's got those 3 roots that you could find by factoring. We've seen this before. We've sketched it. We've looked at it in a calculus class, in an algebra class. We've seen it before. All right, if we look at different outputs and this is also kind of go into the idea of a horizontal line, and I will connect these with the idea of the preimage at the end. But if we look at any y level and we go off and draw a horizontal line, we're going to hit graph at least once. Okay, this one hits it 3 times, but it's actually not important, how many times. It says for at least one element of the domain. Okay, if I go up, I'm gonna hit some graph, and if I go down, I'm gonna hit graph. And it's no matter where I go, I'm gonna hit graph because the way those arrows are pointing in opposite directions. Okay, so this graph is surjective. It covers the whole real numbers. There's no real number where we're not going to be able to find at least one piece of graph. And so it is the case that all odd degree polynomials are surjective onto the real numbers. But an example of a function who is not surjective would be secant x. G of x equals secant x. I could have also done sine and cosine, but I just thought secant, it was really easy to see from the graph that this is not covering the whole set of real numbers. It's covering most of the real numbers, and that's kind of the issue with sine and cosine, is that they're covering such a limited range that it's not even close to being surjective. This has got, a pretty big range, but if I draw that horizontal line over there near the x-axis, I think between y equals -1 and y equals 1, I'm going to come up empty. I'm hitting no graph. And so I cannot say that secant x is surjective onto the real numbers. Okay, now, a lot of this does have to do with, your definition of A and B, your definition of your codomain, because if you just say, say the function 1 over x. If you say the domain and the codomain of that are the set of all non-zero real numbers, then you could say that 1 over x was surjective. But if you just have the usual perspective where a function that takes in a real number is giving you back an element of the set of real numbers, and that's your codomain, this would not be surjective. All right, now connecting this to the idea of matrix algebra, if we're thinking about every element of the codomain is mapped to, that means the column space is going to fill up the whole, have the maximum possible number of dimensions, or there's never no solution. It's always consistent. Okay, we could have infinitely many solutions, but we can never have no solution. Okay, so this is kind of the opposite of what we were talking about earlier, where we could have no solution, but we can never have infinitely many solutions. Okay, so we'll say that a linear transform, which takes Rn into Rm, which is defined by T of x equals Ax. A is that standard matrix, which is an m by n matrix. We'll call it onto or surjective if Ax equals b, the associated linear system of equations, is consistent for all b in the codomain. And our test for whether a linear transform is going to be onto or surjective is T will be onto if the rank of the matrix is equal to M. Like the same M from Rm in the codomain. Okay, and so my commentary on that is if AX equals B always has at least one solution, never has no solution, then the column space of A is all of Rm. And that might be self-evident to you just thinking about the matrix algebra, the way you think about it. But if it's not, I might try to convince you of it thinking about, okay, well, A is a matrix that has M rows and N columns, okay, because it's an M by N matrix. And that means that the columns of A, each column, is M entries tall. And that's an important thing to understand, right? That's why the column space is, it kind of seems the opposite of what it should be. But if you think about it, it's exactly what it should be. Okay, that means that the column space of A is a subspace of Rm. Okay? But if AX equals B is consistent, that means B can be written as a linear combination of the columns of A. We've seen that over and over again in this semester. Okay, which means that B is in the column space. Okay, so every vector in Rm is in the column space. That means that the dimension of the column space is M, because the column space is all of Rm. Okay, and that dimension of a column space, that's the definition of rank. So we've got the rank of our associated matrix is M, and that means if we've got, the rank is the number of pivots, and M is the number of rows, we are looking for a pivot in every row. If we've got a reduced row echelon form and we're trying to decide if the associated linear transform is onto or surjective, we're asking ourselves, really, is there a pivot in each row? And putting these two ideas together is the idea of a bijection, or a one-to-one correspondence. And so our definition is saying, okay, F which maps A into B is a one-to-one correspondence, or bijective, if F is both one-to-one and onto, both injective and surjective. And this example is actually a relatively simple one, but I think it's like I need to be clear about the way bijections work, is that they're like, it's a perfect match. It really is a more accurate description of one-to-one, in my opinion. But f of x equals 2x is definitely going to be a bijection, because at each output, I am hitting exactly once. I'm hitting graph exactly once. That's kind of the thing with a bijection or one-to-one correspondence, is that there's going to be exactly one input corresponding to each output. And so another thing about a bijection is that they have nice inverses. Now from the algebra classes we've taken along the way, we're familiar with solving for the inverse of exponential functions, logarithmic functions, square root functions, polynomial functions, and sometimes they have like restrictions on them, right? Trig functions. We see where, like say the inverse of x squared has restrictions on its domain. Okay, we can't plug certain negative numbers into square root because of restrictions on the output of square. And the reverse can happen too. But bijection is a function where the inverse is existing and it's unique and there's no restrictions on the inputs or the outputs. And so I'd say this is an example of bijection. But taking it to the idea of a matrix, it would be that a linear transform is bijective if the associated linear system of equations has a unique solution for every b in Rm. And so if we always have a unique solution and never have no solution, that actually means our matrix has to be square. Because we can get a unique solution out of a tall matrix, but we can also have no solution out of those very easily. I think you've row reduced enough matrices along the way this semester to know how that's true. And so our test for if a linear transformation is bijective, it's going to be, is the associated matrix non-singular? Okay, because it's got to be a square matrix to even have a chance to be a bijection. And if A has a pivot in every row and every column, that means it's row equivalent to the identity matrix, right? And if the reduced row echelon form of a matrix is the identity, that means the matrix is definitely square and it means it's non-singular. Okay, now that's really all I have to tell you in this video, but I do want to go in and connect this to the idea of the pre-image, because you saw over and over again with those graphs, I was going up to the y-axis and looking across, and so there was really that pattern there. And if you've been in my class for a while, which this year I've got some people that have been in my class for quite a while, you've gotten a kind of an inverse functions talk from me at least once a year. And I think that this is a really, really important topic. This is another one that just like kind of weaves all the way through all the math courses that you're ever going to take, is the idea of a function and an inverse. And so, if you've heard, or it's been a year, or it's been a while, I'm going to remind you that if f maps A into B, then the pre-image of an element B in the codomain under f is the set of all elements in the domain that map me to that given output. Okay, so like if f of x equals x squared, f inverse of 9 is 3 and negative 3. It's a set. Okay, and I think this is the best idea of the inverse, is the pre-image idea, but that's just my opinion. I'll get moving on 1-to-1 and on 2. So for 1-to-1, f inverse of b has at most one element for any b in B. So if I'm thinking about e to the x, this one's a yes. Okay, I would say, all right, f inverse of, let's say, 1, that's where I set e to the x equals 1, and that's x equals 0. F inverse of 1 is just the set that has 0 in it. I can try f inverse of like negative 1, and I say, okay, e to the x equals negative 1, and I'm going to come up empty. Okay, so that's the empty set there. But I'm never going to get a set with 2 elements in it when I'm trying to look at the pre-image of an output of e to the x under that function. Okay, on the other hand, absolute value x doesn't work like that. If I try to look at, say g inverse of 5, okay, that would be setting absolute value x equal to 5 and solving for x. That's x equals 5 and negative 5. And that is a set with more than one element in it. So this function is not 1-to-1. It's not injective. Okay, and then if I'm thinking about onto, that's where when I pull back, when I look at the pre-image of some number under the function, it always has at least one element. It's never empty. Okay, so f equals sine x was not onto, right? Because it only maps onto the interval negative 1-to-1. Those are the only possible outputs I can get. And if it was going to be onto, I could be having any possible output. That's going to be tangent. Okay, so for this one, I'm going to say, all right, well, f inverse of 2, that's where I'm looking for sine x equals 2, and I'm going to come up empty there, right? There's no possible way, there's no angle that I'm going to get sine of x equals 2. It's not possible. So I'm going to say that sine x is not surjective. Okay, but tangent x, g inverse of 1, I know what that is. Arctangent of 1 is pi over 4, tangent x equals 1. Well, I guess there's more than just pi over 4. Yeah, this is equal to, I think it's pi over 4 plus pi n, where n is an integer. Okay, but it's not a problem that I got more than one value back. Is that even, that is still visible to you. I got at least one value back. And if you think about the graph of y equals tangent x, it's got those vertical asymptotes. It goes up and down forever. And also the graph of arctangent goes all the way to each side. You can put any number you want into arctangent. And so that one is surjective. It is onto. All right, and then my last example is a 1-to-1 correspondence, obviously, and a great one of this is x cubed, right? Because it's got a really nice, well-defined inverse. I already did the linear example. I'm going to do the cubic example. But if I'm interested in finding, say, like f inverse of 8, I'm going to say, okay, x to the 3 equals 8. That's x equals 2. So f inverse of 8 is equal to just the set that has 2 in it. But I can see I got that 2 by taking the cube root of 8. And we know that for any output y, f inverse of y is equal to the cube root of y. And there's no restrictions on what we can put into cube root or get back from cube root. We can take the cube root of a negative number and it gives us a negative number. It's great. Okay, and that's what I'm talking about with a one-to-one correspondence. Okay, with a one-to-one correspondence, the pre-image of a given output is always existing and it always has exactly one element in it. All right, so that's all I got for you for this video. Thanks for watching.